How do we invent a new paradigm? In fact, it's not an arbitrary thing. It can be very natural and very systematic. So there's a particular rule involved here. When in a given paradigm, the programs start getting complicated for technical reasons that are unrelated to the problem being solved, then this means there is a new programming concept waiting to be discovered. And if you add this concept to the kernel language, then your programs get simpler again. So if you start programming something and you notice you're building things, but it's sort of unrelated to the problem, well then that means that your design needs another concept. You just have to figure out what it is. And we saw one example of this, concurrency. So assume that you're programming any sequential paradigm with no concurrency, and you need multiple independent progressing activities. If you need that, you have to implement many things. Each of these activities needs its own execution stack, you need to have a scheduler, and so on. And if you start implementing all that, if you would just add concurrency to the paradigm, then the programs get simple again. So let me give another example of this, which is exceptions, which we saw also in this course. So if your paradigm does not support exceptions, for example, like in C, then all routines that are on the path between two procedure calls, procedure 1 calls 2, 3, 4, and so on, all of them have to create error codes and test error codes of all the procedures they call. So your program gets very complicated. But if you do have exceptions, for example in Java, only the ends, the first procedure in the whole chain and the last one, need to do anything special. So here's an example, particular example. So on the left I have a language without exceptions, on the right I have a language with exceptions. So on the left I have procedure P1 calling P2, P2 calling P3, P3 calling P4, and P4 here, and P4 detects an error. Now each of these procedures, P4 has an error code, E4, and P3, when it calls P4, it has to test this error code. P2, when it calls P3, has to test the error code, and so on. So there's a whole bunch of error code handling going on in all the procedures on the call path in order to handle the error that occurs in P4. On the right-hand side, things are much simpler. P1 will use try to create an exception handling context, and then it calls P2. P2 calls P3, no error codes needed. P3 calls P4, no error codes. P4, as before, detects the error, and this time all it has to do is erase. So the erase will immediately cause the execution to go to the innermost and closing context, and the procedures in between here are unchanged. So the program becomes much, much simpler. So this is why that the concept of exceptions is an important one to add. So if you look now at the complete set of concepts, so here I have a table with a complete set of concepts that are all part of the paradigms explained in the CTM book. So in this course, we've only seen a few of them. I've classified them. The first part here is descriptive concepts, creating records, numbers, procedures, creating data, in fact. The second part is everything that is declarative execution, if, case, procedure call, threads, and wait needed. So thread for deterministic data flow, and wait needed for lazy deterministic data flow, a paradigm which we have not seen in this course. And the final part here is other concepts that are needed for more sophisticated or different paradigms. For example, the names, which are unforgeable constants, so they can be used for making things secure. In fact, the secure abstract data types need that. There's also a read-only view for building abstract data types which have unbound variables as output. Then we have exceptions. And then we have ports, the simple named stream communication channel. And the final concept here is a little bit different, is spaces. It's still a little bit complicated. I only give the name here because, in fact, it's probably not yet completely understood. So this is one way of organizing all these concepts into a kernel language which encompasses all the paradigms of the CTM book. Another way to see it is to, instead of ports, to use cells. So notice, instead of new cell exchange, we can have new port, new cell exchange, or we can have new port send. We can either the other, they're in fact equivalent. Each one can be implemented in terms of the other. So normally, in terms of simplicity, we will assume that the ports are the basic concept here. So this is one way of building paradigms, of creating new paradigms. Each of the new paradigms which has been created here has been created according to the creative extension principle. When we feel the need, when things are happening in a program that show that a new concept is needed.